or the network models. So one such model is the maximum flow. Maximum flow, which is used in traffic management, which is used in crude oil pipelines, which is used in logistics and supply chain. So this maximum flow is a graph theory model. It is a directed graph. It is a directed graph involving a source denoted by S and a sink denoted by T. And several other nodes will be there, and several other nodes will be there. Connected with edges. Connected with edges, and each edge has an individual capacity. Each edge has an individual capacity, which is the maximum limit flow, which is the maximum limit flow that edge could allow. So there is lot of edges, and each edge has an capacity, which is the maximum limit flow that can be allowed. Now, if you look at this one, the example of this methodology will be maximum flow So if you look at the diagram, this is what I mean. The origin is 0, source is 0, sink is 5. And there are a lot of nodes and edges. And in terms of edge has an individual capacity, which is the maximum limit flow of that model. So this is what so each edge is labeled with a capacity, the maximum amount of that it can carry. The goal is to figure out how much stuff can be pushed from vertex to vertex, which is source to sink. How much is possible to be moved from one source to the sink. So based on the nodes and graphs given here, we need to find the maximum flow approach. And if you are looking at the algorithm, which is very popular, is the Ford-Fulkerson algorithm for maximum flow. So this is a very popular algorithm which is used, Ford-Fulkerson algorithm for maximum flow problem. So there are certain constraints. Flow on the edge does not exceed the given capacity of the edge. Incoming flow is equal to outflowing flow for every vertex except S and T. So the conditions are these. These two are the conditions. Flow on the edge does not exceed the given capacity of the edge, and incoming flow is going to the outgoing flow in a single manner. So this is your maximum flow method using Ford Fulkerson problem method algorithm, which is a popular algorithm which we are going to discuss today. So the Ford Fulkerson algorithm is very popular in maximum thing. So it's simple. Start with initial flow as 0. While there is an augmenting path from source to sink, add this path flow to flow, return the flow. So it's a simple algorithm, but when you implement it, it is slightly little bit what you call calculation oriented. We'll try to make it as simple as possible. So this is the maximum flow problem which we are going to discuss today. So like I told you, there are constraints that you cannot have flow maximum than the limit, and whatever goes inflow, the same thing will come out as outflow. Okay, so it starts with the what we call by initial flows making 0. So let us look at the problem and try to solve it using the maximum flow manual method. So using the Ford Fulkerson algorithm. So there will be something called residual graph is also created. One more thing we need to understand is the concept of residual graph. So I think this is the same problem we are looking at. The solution is given here, A, B, C, D. Residual graphs. So residual graph definition is not given here. Let me see where we get the residual graph definition. All right. This is not me. I think this is a simple problem. Let us do this problem compared to the jumping into the complicated one. We will use this problem. The flow network above. So you have S to T, source to sink. So you have S to A is 3, A to T is 2, A to B is 5, S to B is 2, 3. So you will start initially set the flow along every edge to 0. So the first step is to set every edge to 0. These values 0 by 3, 0 slash 3, 0 slash 2, 0, 5, 0, 2 and 0, 3. Use a path finding algorithm like depth first search or breadth first search to find a path from P to S that has the available capacity. So let capacity P indicate a maximum of stuff that can flow along that path. Okay, to find the capacity, we need to look at all edges and subtract their current flow from their current capacity. So what we are trying to do is we have taken 3 as the current flow, and we added it from 3 by 3, 3 by 5, 0 and 2. You can't do anything here. The limits are smaller than the flow. This is 3 by 3. So S to A to B, and B to T. So we can say then we will use 2 by 2 and 1 by 5 suboptimal flow of 3. So this is the concept of residual graph. So this is where the fourth Fulkerson algorithm is starting. So initially we will set the flow along the edge to 0, 0/3, 0, 2, and we have the residual graph. This is called the residual graph. Now, once we have the residual graph, run through the algorithm, find we can achieve a flow of 3. So we can achieve a flow of 3 here, 3, we can achieve a flow of 3 here, we can achieve a flow of 3 here. We cannot achieve any flow of 3 here because there is a limit of 2 here. So we'll update the residual graph by putting the opposite arrows. 3, from here to here 3, from here to here 3. So such to the updated residual graph for a new path S to 3, there are no forward edges available anymore, but we can use a back edge to augment the current flow. We can decrease the flow by 2. So we have 5 here, we have decreased it to 2, and then we will use the 2 as the edge thing. So 2 by 2 and 1 by 5. And then we can draw the arrows accordingly. There are no with available capacity we can use S2T. This means our max flow T is 5. Okay. So let us update. So this is our flow. What we are doing is we are first setting up the flow to 0. We are setting up the flow to 0. So this is S, this is A, this is C, this is B. So we have a path here 0/3. We are setting the flow to 0, 0/2, and then we have a path to T 0/3, and we have a path here again 0/2, and we have a path here 0/5. So we have initiated the set flow along every edge to 0. This is the first step. Okay. So we have initiated the first step as 0. Initiate the flow with 0. Now what we have to do is we have to find what we call the residual graph is already constructed. This is our residual graph. This is our residual graph. So now we can see where we can achieve a flow of 3. So we will see wherever we can achieve the flow of 3, because 3 looks like to be the maximum flow outside the edges. So we will go with 3 as the flow, and then let us update the network by maximum what we call achieving a flow of 3. This we can achieve flow of 3 by 3. Here we can't achieve because the limit is 0 and 2. Here we can't achieve, it is limit of 2 by 2. Here we can achieve the limit is 5, so 3 by 5. Here it is 3 by 3. So from
Sir,
this,
why are we choosing 3, sir?
maximum outside edge, maximum of the outside edge.
Okay, sir.
Okay, maximum and see, what is the maximum amount that can flow along the outside path? 3, right? There is outside is 2s and 3s. So
Yes, sir.
the maximum amount of steps that can flow along the path will be the P, cap of P. So we are taking 3 as the cap of P. Okay, and then we have seen by taking 3 as the maximum flow, how many paths can be achieved. We can't send it between the SB because the maximum limit is 2. Between E and T was also not possible because the maximum of 2. The other 3 we can achieve with the maximum of 3. So we will rework our residual graph. So the residual graph will be reworked A, B, T, and S. So the initial was this, so this to this to this, and this is the arrows, right? This is the initial. Now we will draw a reverse arrow. Okay, this will become 3, this will become 0. Similarly, we will draw a reverse arrow where we'll have 2 and 0. Similarly, we will draw a reverse arrow here where we are splitting it 2 and 0. Here we are drawing a reverse arrow 3 and 0. And we are also drawing a reverse arrow here as 1, 4. 1, 4. Okay, okay. Sorry.
Sir, can you repeat?
No, 1 second. I think I've drawn the wrong graph. So, 1 second. I think I've jumped a step here. Let me just correct it one more time. Let me check one. Yeah, I jumped a step. 1 second. Once we set the initial flows to 0, then the maximum will be 0. This is the wrong graph. Sorry, I jumped a step. So the residual graph is A to B to T and to S. This, and this, and this. Right. So we will draw a reverse graph 3 and 0. We will draw a reverse graph 3 and 2. Let it be 2. Let this be 2. We will draw a reverse graph 3 and 0. 3 and 0. Or you want me to draw them as a different one? This is the reverse graph. This is a reverse graph. And this is a reverse graph. 3, 3, 3, and 2. So we have drawn a reverse graph with the flow of. Now we have to search through the updated residual graph for a new path. We have to search through the updated residual path. This is our updated residual graph from which we have to search for a new path. Now, if you look at the available limits, 2 is the available limit, right? 2, there are no forward edges available. There are no forward edges available with what you call, most of the forward edges are 0. So what we are trying to do is, sorry, this is the wrong edge.
Sir,
Since all
sir, how are we writing that 3032? Is it like 3 is the value of the reverse path and the other one will be different?
the flow will be, see, the inflow is equal to outflow, right?
Yes, sir.
Inflow is equal to outflow. So when you made the initial flow 0, that means whatever is done, we have to take it as outflow, right?
Yes, sir.
We initiated the inflow as 0, right? And then we found out the maximum flow, and then we have made them 0. The inflow will be 0, the outflow will be the replacement one, which is 3. So the size of the flow in the edge is 3 only. The maximum limit is 3, right?
Yes, sir.
So that is how we have done. So we have updated the residual graph with the backward flows. So we have to now search for an updated path in residual graph. But there are no forward edges available anymore, but we can use the back edge to augment the current flow. So we can decrease the flow along AB edge by 2, which will allow us to make use of both edges leading to it. So there are 2 edges leading to the AB edge. So what we can do is we can make them equal to 2. The residuals are 2, right? There are 2 edges which are leading to B. One from S, the other from S. Both are equal to 2. So we can take 2 as the parameter and we will update the residual graph. The updated residual graph will have A, T, B, S, right? So this will be 0. The backward path is 3. There is a straight path 2 by 2 because we are taking 2 as this one. So this path, there is a 2, there is a 3. So this we can make it 2 by 3. Here there is a path 2 by 2 and here there is a residual path 3 and the path is 0. So we have updated
Sir,
with the...
Can you repeat, sir, what we did in this?
So what is the other number left for the forward path? What is left for the forward path? Forward paths are these arrows, right? Black arrows. Red arrows are backward paths, right? Red arrows are
Right.
backward. So what is left for forward path? 2.
2.
Right? 2, 2. So we are taking 2 by 2. Maximum flow is 2. We are taking the maximum flow as 2. And this side also we are making 2, 2 as the maximum flow. Here this side the forward path is 2 by 3. And again we will update the path. So we will augment the path again. Okay, with the residual graph. So this is the residual graph. We will upgrade the path again using this residual graph. So based on this top updated residual graph, A, B, T, and S, this will become 3 by 3. This will become 2 by 2. This will become 1 by 5. This will become 2 by 2. This will become 3 by 3.
Sir, again, I have a small doubt.
Yeah, please go ahead.
Sir, why didn't you make 2 by 3 in that, from this thing, the other one? So like you have written 2 by 3 and 2, right? In the middle part. So why haven't you done 2 by 3 in the other part also?
See, basically, the path value 5 actually should be 3 and 2, right? We can do by 2 also. So it's a simple edge calculation usage. We are trying to use the maximum flow. The formula is based on the maximum flow, right? Among 3 and 2, which has the maximum flow?
3.
3. So I am choosing the maximum flow option here. So we are choosing the maximum flow option, right? So that is why we are choosing it as 2 by 3.
Yes, sir.
Got it? Based on the maximum flow concept.
Yes, sir. So, like the other trees are there, right? We will not touch that.
Which one? They are already filled up now.
So we will not touch the reverse path 3.
We will not see either the inflow will be 3 or outflow will be 3.
Yes, sir.
The maximum limit is 3 now.
Yes, sir.
So we can't touch them. See, based on this, what were the forward arrows left out? This is the forward arrow. 2s are left out, right? Forward arrow. And we have
Yes.
this interlinking arrows where we have 3 and 2, the inner edges, going towards one another. In this is the maximum flow. I say we choose this 2 by 3 and I left the 2 like this. So finally, total is 5. So 1 by 5 is left out. We have taken the, what we call 4 units, and then we maximum is 1 unit is still left out. So that I representing it as 1 by 5. 1 or 5. 1 or 5, not by 1 or 5. Now, based on this, we will create our final thing. So, this is your A, this is your B, this is your T, this is your S. So, we have a straight path of 0 and a reverse path of 3 here. Okay? We have a straight path of 0, a reverse path of 2 here. Okay? Now, we have a straight path of 0 and a reverse path of 2 here. Similarly, we have a straight path of 0 and we have a reverse path of 3. Similarly, we have the path here to 4 and the reverse path to 1. Now, there are no forward paths available, right? There are no edges with available capacity. So, there are no edges with available capacity that we can use to create a path from S to 3. That means, what is the path, shortest path? From S to B to T is how much? 3 plus 2, 5. Right? S to A to T, how much? Again 3 plus 2, 5. Right? So the maximum outflow and inflow path is 5. Even the inner workings are also 5. Right? This is also 5. So the maximum flow is leading to T is 5. S to T maximum flow is 5. Got it? Or let us see a video. All your doubts should go off by that time. Sometimes the videos help us. How to add audio here? I forgot.
Sir, when you share the screen, you will have the option of use audio also. So you need to reshare this.
Okay.
Sir, you cancel that first. The
Pardon?
screen share. So there is, so beside the mic on the right hand side, you have a cross mark, right? Just click on that. Right. Now, when you reshare, you just click on use audio, share audio also.
Where is it? Include computer sound. Huh?
Yes, sir, in the same symbol.
Okay.
Trying to find the maximum flow from a source node to a
Yes, sir,
sink.
it is audible.
We'll do this by finding augmenting paths from the source to the sink.
I'm on
An
the
augmenting
maximum
path is simply a
volume.
path whose edges are either non-full and forward or non-empty and backward. Basically, a path that still has capacity for flow. You'll see exactly what I mean by this in the example. Here's the flow network we'll use. S will be our source and T our sink. We'll start by setting the flow to 0.
Hey, the voice is very low, right? How to increase the voice?
Sir, it is audible.
Left is the current flow through the edge, and the number on the
So,
right is the
guys,
total.
first thing you
You'll
need
see
to
exactly
understand is, sorry,
what I mean by this in the example.
I'll explain, don't worry.
Here's the flow network we'll use. S will be our source and T our sink. We'll start by setting the flow to 0.
So this is the first thing you need to understand. These are not division. 0 is flow, 4 is capacity. Is this clear now?
Yes, sir.
It's not division. 0 slash. 0 is flow, 4 is capacity. What is capacity? Maximum amount of flow that can occur between A and B. Is it clear?
Yes, sir.
So the maximum capacities are given in numbers. We have set the initial flows to 0. Okay. So we find an augmenting path, compute the bottleneck capacity, augment each edge and the total flow. So the path can be S to A to D, and D to T. So what is
Sir, the audio is not there, sir. Again,
see, now you can hear me.
sir, I can hear you, but not the video's audio.
Video audio is very weak, so I am explaining. See, what we did is we found out a path here. S to A to D, and D. We took a random path. Okay. And in this path, what is the lowest value? In the red color path, what is the lowest value?
8.
8, right?
Yes, sir.
So we have find out the lowest value in the augmented path. So this is the path we have found out, SADT, and in this path the lowest capacity is 8. So we have deduct the 8 from the capacity for this augmented path. So your terminal path will become 8. 8 by 10, 8 by 8, and 8. Now we are going to the second path. Second path can be between S to C, C to D, and D to D, T. Okay. The second path which we can take is S to C, C to D, D to T. What is the lowest amount of this? 2. Because 2 is only left here, right? So we have
Yes, sir.
exhausted the capacity here. We have taken 2 by 9, 2 by 10, and the final path is by 10. Then we have other paths also. S to C we have full some residual. 8 to 8 we have some residual. 0 to 4, 0 to 10 some capacities are left out. So the lowest of this is 4. So we taken 4 by 4, 4 by 8, and 6 by 10, 6 by 9, and we have added this to 14. 10 to becomes 14.
Sir, can you re-explain the steps, sir?
I'll explain one more time. Yeah.
and augment the flow. We now have a flow value of 19. One more time, let's search for a path. Looking at S to A, we can see the path is full. Now looking at SC, we notice we have a capacity of 1. However, the forward edge CD is full, and the backward edge CA is empty, so we cannot augment the path. Since we cannot find a path from S to T, our algorithm is done, and our final flow value is 19. Don't be worried if you chose different paths than I did. Even
but we can still go, right? From S to C, C to... Okay.
Let me see if I can get another video, okay? This can explain. This is a 5 minutes explanation.
Yes, type 2 diabetes can be reversed.
The thought that I would. हेलो फ्रेंड्स, हम सॉल्व करेंगे आज मैक्सिमल फ्लो प्रॉब्लम। क्वेश्चन आपको कुछ ऐसा दिखेगा एग्जाम में, या फिर आप जब भी सॉल्व करने जाएंगे तो आपको कुछ ऐसा क्वेश्चन दिखेगा। क्वेश्चन ये होगा कि आपको नोड 1 से लेकर नोड 7 के बीच में जो
I think this is Hindi. You don't want Hindi. I'm looking for a smaller video which can explain us the simplest manner.
Hello everyone, today I'm going to talk about the Ford-Fulkerson algorithm for max flow, what it's used for, how it works, and analyze its complexity. So first and foremost, what problem does it solve? As we said...
You guys are able to hear?
Yes, sir.
Something is voice is very low, yeah.
Sir, I just want to see, sir, what was the answer for the problem that you solved?
15. Sorry. 5.
5, right? Sir, I think I got it. Like, we have to just see the path wherever there is capacity and we have to add, right?
Yeah, that's what. Wherever the capacity is there, to be utilized.
Yes, sir, because that video was trying to explain this only.
Yeah, the whole thing is we need to utilize the flows and achieve the maximum flow using the capacities. Using the capacity,
yes, sir.
Maximum flow. That is what I am trying to do. Can you guys hear loudly?
Yes, sir, not audible.
Very less, na?
About flow networks is everything that comes out of.
Now it's audible.
Let me see if I can move from the tab mode to PC mode, then it will work. me see if you can work with. So all of them are in maximum only.
From V1 to V3, V3 to V2, and V2 to V1. Pump 13 out of the source must be equal to the amount that comes in at the sink. So if we pump a total of, say, 7 litres of water out of the source, then 7 litres of water must be returned into the sink. This is obviously limited by the interim weights. What the max flow problem is what is the maximum amount we can pump through this network? And this is what the Ford-Fulkerson algorithm solves. So we're going to go through a worked example of the Ford-Fulkerson algorithm. As you can see from the algorithm in front, what the Ford-Fulkerson algorithm does is, while a path exists from the source to the sink, say we go from the source to V1, V1 to V2, V2 to V3, and V3 to V4, and V4 to the sink. While such a path exists, the Ford-Fulkerson algorithm says, calculate the residual network of that path, and then repeat. You may be wondering, what's a residual network? Well, I'll show you in this example. So first of all, we find a path from the source to the sink. So we go from the source to V1, to V2, to the sink. We can clearly see there's a path. In order to pump water along this path, we have to choose the smallest value, which in this case is 3. So we pump 3 litres of water from the source to V1, V1 to V2, and V2 to V3. As we have pumped 3 litres of water along this path, that means 3 litres of water has been pumped along here, so we will label this as 10 of 13, 2 of 5, and 0 of 3, because that is the residual amount we have left. We then draw a backwards labelled arrow, stating how much we have pumped through that already. We've pumped 3, we have pumped 3, and we have pumped 3. Here is therefore what the residual network looks like. Next, as Ford-Fulkerson states, we want to continue this until no such path exists from the source to the sink. So we'll pick another path. For instance, source to V3, V3 to V4, and V4 to the sink. We are able to pump 10 litres of water along this, as 10 is less than 35 and less than 20. So we pump 10 litres across here, leaving us with none left, and a backwards arrow of 10. We pump 10 litres, leaving us with 25 of our 35, and a backwards arrow of 10. And from the sink to V4, with a backwards arrow of 10. So far, we have pumped 3 and 10 litres of water. Again, as Ford-Fulkerson states, we try and find another path, and there is one available. If we go from the source to V1, V1 to V2, V2 to V3, V3 to V4, and V4 to the sink. So we'll do that. We still have our remaining 10 we are able to pump here, 2 we are able to pump here, 50, 25, and 20. Obviously 2 is the least of them. So we pump 2. This will therefore become 8. This will become 5, as we are pumping 2 extra backwards. This will become 0. Again, 5. This here will become 48 of 50, with a big backwards arrow of 2. This will become 23, and this will become 12. This will become, again, because we're pumping 2 litres of water around our system, and this as well will become 12. So we pumped another 2 litres of water around our system. If we go back to the algorithm, it says, well, no such path exists. So we look at our graph again. We can tell that there are no paths exist, as if we go from the source, we cannot go this way, as there is 0 room left to pump water. We go this way, we're able to pump 8. But unfortunately here, from V1 to V2, again there is 0. So there is no path left from the source to the sink. Therefore, the maximum flow of our network is 15. and this satisfies our condition at the very start that whatever leaves the source must enter in at the sink. If you're wondering what the increase max flow counter of the algorithm does, this is simply a variable that holds the total sum of all the max flows of all the paths throughout the whole graph, i.e. this part of the worked example. I've included this section in the video as I simplified the working example to make it easier to understand, but you'll hear a lot of these terms thrown around online. For instance, augmenting paths. What is an augmenting path? An augmenting path is simply the path we take from the source to the sink, as seen here in the worked example. The residual capacity. The residual capacity is the capacity of an augmented path. So in other words, it is the total flow pushed along that path. And lastly, residual network. I briefly mentioned earlier what this was, but just to recap, here it is again. It is really the resulting network after the augmented path has been applied. The time complexity of this algorithm is E times the maximum F, where E is the total number of edges, and max F is the maximum flow that we would calculate using this algorithm. Okay, so I'm going to quickly draw a graph. With the source to the sink at the end. These with weights 500, 500, 500, 500, 1, and 1. So I'll switch to the red pen. As for Fulkerson algorithm states, we need to find path to augment. A best case scenario would be if the algorithm chose S to V1, V1 to T, or equivalently S to V3 and V3 to T. But worst case, our algorithm chooses S to V1, V1 to V2, V2 to V3, and V3 to T. In that scenario, the minimum capacity of the augmented path the algorithm chose is 1. Therefore, through this, we'll pump 499, the backwards arrow of 1. Through here, this will come 0. And we'll pump 1 back. This will become 0. We'll push 1 back. And this one here will also become 499. And we'll push 1 back. Next, the algorithm may choose S to V3, V3 to V2, V2 to V1, and T. This will become 499. In case I didn't make clear earlier, you may traverse the backwards arrow you have created in your residual networks. So this will return back to 1, while this becomes 0. This will return back to 1, as this becomes 0. And this will become 499. Again, with a backwards arrow of 1. You may see a pattern that has developed. We may now keep continuing this pattern of going from S to V1, V1 to V2, V2, V2 to V3, and V3 to T, and then do S to V3 to V2 to V1 to T. The maximum capacity of the entire flow of the network will increase by 1 on every iteration. And this will keep happening until all 1000 has been pumped out of the source. So we'll call that T0 as well. Lastly, when...
Shall we do this example one more time to understand further our concept?
Yes, sir, we can.
Yes, so we will do it. Because I think the tab mode is the problem. So every time I have to play a video, I have to move it back to the normal mode. Okay. So in the example, so this example thing, if you look at this is your source. We have V1, we have V2, and then we have the T, which is our sink. Okay, and we also have 2 here, which is your V3, and we also have one more, which is your V4. So the path goes from here to here with a capacity of 13, V1 to V2 capacity of 5, V2 to sink capacity of 3. Similarly, V2 to V3 we have a capacity of 50, and then sink to V3 we have a capacity of 10, V3 to V4 we have a capacity of 35, V4 to V5 we have a capacity of 20. Okay, so initially we will start with S to V1 to V2 to T. What is the lowest here? The lowest capacity is 3, right? So we will draw a reverse arrow, assign 3, and we'll make this 0, right? Similarly, we will assign a reverse arrow, we will make this 2. Similarly, we will assign a reverse arrow, we will make this as 10. Right? Then we have one more path which goes from the other path is S to V3 to V4 to T. Right. What is the lowest of these three? 10.
10. 10.
10, right? So the low cap is 10. So we will draw an arrow 10 and we'll make this 0. We will draw an arrow 10 and we'll make this 25. We'll draw an arrow here. We'll make this 10 and 10. Right?
Yes, sir.
Now we have one more path which is S to V1 to V2 to V3, V4 and V5. So already we have get what 3 plus 2, right? So we have already set up, we have used 3 plus 10. The floors we have used is 3 plus 10. Now we have another path. This is our first path. To see the diagram, this is our second path which we have done. Now we will set up the third path.
So the third path, lowest
is from
capacity
S to V1
2,
to
right?
V2 to V3 to V4 to T, right? And what is the lowest of all these things?
2, 2.
2. The lowest of all this thing is 2. So that means we have to deduct 2 from all of them, right? So we will make this 0. We will make this 8. Okay. And then this 50 will become 48. And this 25 will become 23. And this 10 will become 8. Right? So we have added plus 2. And we don't see any other paths, right? All the paths have been fulfilled. So the final maximum flow is 15. So the final maximum flow is 15. Got this?
Yes, sir. Yes, sir. The last time it was confusing. Like,
Pardon?
this time it was. Last time when you did, it was a little confusing.
Yeah, now this is very clear, right? After seeing the video.
Yes, sir.
See, last time one also, we can simply do it actually. What was it? I'll just repeat the last one again. S to A to T. We can manually do it. It's a small one, right? S to A. Hey, can you tell me the once more time the values? S, A,
S,
T,
A, B,
and
terminal.
T. S to A is how much? 3, right? A to T?
2.
A to B?
5.
S to B?
2.
B to T?
3.
3. Now here we will take the initial path as S to A to T. What is the lowest value here?
2, sir.
2, right?
Yes, sir.
So we'll make it 0. This will become 2. This will become 2. This will become 1. Right? So we have used maximum path as 2. Right? Next we have another path S to B to T. Right? What is the maximum here? Lowest here? 2. Right? So this will become 0, 2. This will become 1. This will become 2. Right? Now we have one more path. This plus how much? We have used again 2, right? Plus 2. Now we have a path from S to A to B, B to T. S to A to B, B to T. So what is the lowest path we have? 1, right? We
Yes,
have
sir.
left out
We're getting 5.
1, right? 1, 5, 1 is left out, right?
Yes, sir.
So this will become 0, this will become 4, this will become 0. So we have taken 1. The total maximum flow is 5. Got it?
Yes, sir. So this is only Fort Fulkerson method.
Pardon?
Is this only Fort Fulkerson method?
This is only?
Ford method that you were talking about.
This is the Ford-Fulkerson algorithm. This is the Ford-Fulkerson algorithm. The one which I am talking about is the Ford-Fulkerson algorithm. Oh, I didn't write the name of the algorithm. Okay. So the algorithm is Ford-Fulkerson algorithm. I'll write it here. This is the Ford-Fulkerson algorithm. Got it? So the usage utilities is very high. Ford-Fulkerson algorithm. It is used in traffic management, applications. Yeah. See here, water distribution pipelines, bipartite matching circulation with demands. So these are the applications. Yeah, I think traffic problem is also one flow problem, na? Crude oil pipelines, they use this. Utilities is not given. I saw it somewhere as traffic management also. Yes. Airline scheduling, bipartite matching, survey design, image segmentation. Baseball elimination problem also. Baseball elimination problem also can be done using this algorithm. Is it clear, participants?
Yes, sir.
So, Ford Fulkerson algorithm is used for various purposes.